Hello, this is a small request with another annual upload on my ASMR channel. It's been a while again, I'm sorry for that. But today I'm here to ask a question. What is sound? That is an interesting question. We all know what sounds are if we have heard them. But do we know how are they produced? How are they perceived? Things like that. Well, I'm here today to maybe try to give a little explanation on the science and the physics behind the phenomenon. This is one of the reasons why I ended up studying musicology. So it would be nice to try to also brush up my own memories and see if I can at least try to be factually informative. So let's start by building a room here. This will be a television, which could be the source of the sound in this example. This here is a table, and let's also make a rudimentary sofa over here. There. And also let's build the walls around the living area, like so. So here we have our living space. And let's say that the TV is on here. So the sound will move in waves. That's why it's called sound waves. So we could visualize them if we saw the waves. We could visualize them, for example, if it's a stereo, there will be two sources. But let's for now make it a mono. So there could be a first wave over here. And then another wave here. A wave over there. And let's draw a fourth wave. Might as well. So there are the sound waves. Well, what exactly are the waves made out of? Well, another way to visualize the waves could be with dots. Now I'm just drawing a bunch of dots that are mostly gathered around these parts that we drew the waves in. So these particles here in this sound wave are mostly packed in these wave formations and less so between the waves. And this is actually telling us that the pressure in the atmospheric ambience will be different in the waves than in the rest of the room or between the waves. So what sound waves actually are a differential, a different pressure in the atmospheric ambience. So you could imagine the atmospheric ambience being, for example, like so, that here and there are a little bit of differences in the ambience, but when a sound is formed, it pushes the atmosphere and packs it like so, that it creates these waves. And like in water, these waves don't really like move forward, but more so they oscillate. So they push and retract, moving energy. So sound waves are let's use this pen. Sound waves are a difference in atmospheric pressure. Now, how would we kind of like draw a diagram out of this? Well, one thing we could try to do is first we could draw a line like this, and in this graph let's make another line over here. In this graph, this x-axis would be the distance traveled, and then the y-axis we will call difference in atmospheric pressure. And when the sound comes, this right here is kind of like the stasis, homeostasis, so the normal atmospheric pressure. And here is our speaker. When the sound starts to come from the speaker, it makes these waves. And how does this relate to this picture? Well, over here, the difference in the atmospheric pressure is high. So that would be the waves where the pressure is more dense. And over here we reach kind of like the normal pressure, and over here the difference is to the negative side, so it's less dense than the normal atmospheric pressure of the ambience. So by densening the wave, we are actually making these parts here between the waves less dense than the regular pressure of the atmosphere. So this is what sound waves do when they come from a source. Now, what type of information can we get from a graph like this? Well, actually, quite a lot. Let me tell you a few examples. First, what can we hear in a sound? Well, we can hear loudness, the pitch of the sound, is it higher or lower, and also the tonal qualities. How does it sound? A piano is different from a violin, for example. Well, the loudness will be this right here. So the curve at its apex will determine the amplitude. And amplitude means loudness in this example. Well, what about the pitch? What is the kind of like the how high or low the sound is? Well, that is defined by this curve, the wave, and how many cycles are in a certain distance traveled. So a cycle is the distance from one peak to another peak. This is a cycle. And how many cycles are in a second, or the time traveled, defines what is the pitch of this sound. Let me give you some examples. In a piano, we have something called a middle A. So a middle A is basically above the middle C in piano, so it's also called A4. And A4's pitch is usually tuned to 440 Hz. Now, what does 440 Hz mean? Well, it means 440 of these cycles in a second. And that makes it sound like an A. So these cycles are quite fast and small and tightly packed. Well, what is the kind of like the area of pitch that humans can observe. Human ear usually can detect anything between 20 Hertz to 20 kilohertz, 20,000 Hertz. Meaning that 20 Hertz will be the lowest, deepest sound that we can detect, and 20 kilohertz is the highest pitch that we can observe. So the basses, for example, are usually here around like 100 Hertz, and then bird sounds, some whistle tones, they are more on the 10 to 20 kilohertz area. So if the wave looks like this, it will be a low sound, and then if it looks like this, it will be a higher pitch sound. Now for the third thing that we can perceive in a sound is the tone. How does it sound? How can we differentiate, let's say, a speech from piano to ukulele to cello? Well, that's where the magic happens, and that is a little bit more complicated of a phenomenon. But let's start by I'll make a new graph over here. Let's actually make a graph out of this 20 Hertz to 20 kilohertz thing. So over here would be the lowest sounds, and over here the highest sounds. This is what is usually used in equalizer in music production. You will see something very similar. Let's, for example, draw what the middle A, which is also called a Stuttgart pitch in music theory, what it would look like in this graph. Well, over here we have the 440 Hertz, and this will be the high point of the sound. And this is what we would call the first harmonic of the sound. But this is not the only thing that you can hear in most of naturally occurring sounds. No, this would be the first of these kind of like peaks in the graph. But if we go here a little bit further to 880 Hertz, which is a double from the 440, we will go to the valley, and then there will be another peak. Now what this will be called is the second harmonic of this sound. And what is a harmonic? Well, as you can see, it's double the hertz, so we could call it to be a positive integer of the fundamental frequency, and the fundamental frequency being this 440 Hertz. And then we can go to the next one, like, would it be like 17, 20 hertz? And then there will be another valley there, and then another and another and another and so on so. So a lot of the sounds that we can hear will have these reoccurring valleys and apexes inside them. And these will create different tonal qualities depending how loud or quiet these harmonics are. And these will be different in any different thing, like a voice will have different sets. A unique voice will have a unique set of harmonics in it. So this is what gives the character to the tonal qualities, or the timbre that it's called actually in music, or psychoacoustics. Timbre. And what we have drawn now are these linear curves. Now these don't really occur that much in kind of like a natural environment, but they are part of the kind of like the fundamental building blocks of these waves. Now in electronic music we can have a lot of different type of waveforms. So for example, let's build a few here. This right here is called a sine wave. And then we have something like this, which is called a square wave. Then we have triangles and also something called a sawtooth, which will be like so. That there is a steep or linear rise, and then a steep low and a linear rise, and so on so. So this is a sawtooth wave. Now this can be produced easily with electronic music production tools, but these are also something that can appear in different places in nature, for example. And rarely no sound is just a singular sine wave. That would sound very boring, but what actually makes the sounds is a set of waves. So let me build another example here. First, we would have something like this, but there would be another sine wave which would be a lot tighter underneath it. Well, what happens when there are different type of sound waves? Well, they add up and they will produce something that would look something like this, for example. So for example, when we are talking, it would look a lot more similar to this sound wave here. Now, what we have found out in mathematics and the study of physics is that by seeing a sound wave like this, we can deconstruct it to its more basic building blocks that we can hear or see in these examples. And what this is called is a Fourier transform. And Fourier analysis. It's a complicated equation that I don't remember, but I know roughly how it works. So with this equation, we can deconstruct a wave like this into these rudimentary building blocks, and also vice versa. By having different sets of waves, we can multiply them and end up with something like this. Now, this is what happens naturally in any kind of like a space that we are in. This brings up a lot of different kind of like side effects of sound waves. What happens, for example, if we have a wave like this, and then a wave that is similar but offset by half a step? Well, in some cases, these waves would actually even each other out, making just a line of no sound. And this can actually happen, and this type of an effect is used in, for example, those headphones that kind of like, I don't know what they're called in English, but they deafen out the outside noises. And what they do is they sample the outside ambience, and then they create a loop out of it and offset it by half a cycle of this sound wave. So they even each other out, making quiet. And sometimes when there are two waves that are actually like very much similar, then they will double each other, making the wave very high and also very low in these low parts. So all of these things happen in a very microscopic scale of the universe, and all of them affect, for example, audio recording. So sometimes when you hear something weird happening in the track, because there's like many tracks recorded, it could be because of a wave offset being slightly weird and making these weird transforms in the sound waves. Now let's go back to this first picture that I drew. Now, what happens when there are objects or walls in the space and the sound travels there? Let's continue building these waves. Like so. And then, when the wave reaches these corners or this sofa, there will be a reverberation, Efterklang. And they come from this corner, from this corner, and then from the sofa back to the back room here, and then it reverberates again and again and again. Also, these sofas, they will also work as a kind of like a silencing object, a lot of the sound energy will kind of like stop here, depending on the textures and the materials, but some of it will reverberate back, creating these sets of waves that are traveling across the room to all and each direction. And at the end, this place is full of different set of sound waves. And this happens whether we want it or not. And usually this side of kind of like the science of music and sound is called psychoacoustics. It's the acoustics of the space and how it's perceived by a person there, especially in psychoacoustics. Hey, one more thing I wanted to add to the psychoacoustics is actually the hearing part. So when the sound waves come, we obviously hear it with our ears, and the shape of our ears defines how the sound is perceived. And our ears are very fine-tuned in some senses that we can actually differentiate sounds coming from this side or back from front and whatever. And we can also play around with that, and that's where the binaural beats, for example, come into play. And well, what is the difference between, for example, a microphone and an ear? Well, some of the mechanics behind it are pretty similar. So inside every microphone are these, have to be careful with this. There, inside this foam is what we call a diaphragm. And the diaphragm is this small thing, usually made out of some metal, and it vibrates whenever there is sound coming into the microphone. So it makes these tiny little motions, and those motions will follow through the cable and be turned from analog, meaning that it's actually like a physical difference in space, and transform that analog information to digital information. And that digital information is then used in a computer or sound system or whatever. And our brains are making something similar. So we have these little follicles and membranes inside the ear, and they vibrate, and then they kind of like analyze the sound coming, and then our brain reads that sound into what we perceive as music or speech or cry or laughter or whatever. So this is, in a nutshell, the science behind kind of like the perceived sound of objects and stuff. So back to the rest of the video. A lot of these reverberations will usually be kind of like unwanted, because there's the sound that we have kind of like crafted by humans to sound like something, and then when it reverberates, it can kind of like muddle the first sound waves and create unwanted cacophony in the music or the movie soundtrack or speech or whatever. This could be a person here as well. It doesn't have to be a television. And then we usually want to kind of like work on the acoustics of the place. For example, put something on the walls like foam, or different material on the walls, or some big objects like sofas and stuff like that. And what they do is they make these reverberations that are coming from them be smaller, so they kind of like stifle the sound. And that's what usually we want to achieve in a living space, that there isn't too much of this kind of like an unwanted cacophony created by all these different sets of variables that come into play when we are dealing with acoustics. Now, let's talk about one more kind of like an interesting phenomena in music and sound. Have you ever been in a concert where there are these kind of like loud speakers? This is a speaker, sorry for an ugly drawing, and they are blasting the music, and then your whole body feels like it's vibrating. Ooh. Now this is a vibrating person here. You wouldn't know that I know how to draw. Well, especially when there's kind of like low bass rumble in the sound, your body may start to kind of like vibrate and make you feel even nauseous. Now, what is this called? Well, this phenomenon has a name of resonance. And one interesting thing about existing in this universe is that each and every object has this resonance frequency of vibration. So, for example, each individual human has their own individual resonance frequency of vibration. Let's say that my resonance frequency would be like 307 Hertz. What this would mean is if there is sound coming that has the same 307 Hertz frequency, it would make this object, me, vibrate. And this is fascinating, and this is something that they have to think about, for example, when building new buildings. You may have heard, for example, your windows or the floor or the walls start to vibrate because of a laundry machine or whatever. Well, it's because of this effect. So there is a sound wave coming and our body vibrates because it has the same resonance frequency. And what builds this resonance frequency is our shape, our size, and our mass. And these vibrations may have big impacts. For example, when soldiers are walking on a bridge and they are all going with the same type of a walk pattern, they create these loud rumbles, and these loud rumbles may make the kind of like the structures of the bridge even collapse. And there have been numerous occasions in history when buildings or something has collapsed because of a lot of people creating sound that makes the object vibrate. And nowadays this is a very well-known phenomenon, and it's always taken into account when building new buildings and bridges and stuff. So we don't have to kind of like worry about it. But I bet that in the history of mankind, this phenomenon has kind of like created a lot of even in fears of witchcraft. Maybe this is enough information for now. There could be a lot of different things to talk about, but these were the main ideas, the concepts that I wanted to share with you tonight. And I haven't really kind of like explained these to anyone in my life, so this is also kind of like a way for me to brush up my knowledge and see if I am able to even convey this knowledge forward. And that is one of the most precious things that we humans can do, is teach others when we can and when it's necessary. So maybe this is just me trying to do my part or just trying to find some content for YouTube. Well, I hope you enjoy this. I hope I didn't leave anything out that I wanted to talk about. I guess that's about it. Now, just to sum it up, sounds are waves, and the waves are a difference in the atmospheric pressure of the ambience, the air inside a room. And then there are different types of waves. There are sine waves, then there are triangle waves, there's square waves, there's sawtooth waves. And a lot of the time it's not just one wave, but a multitude of waves. And by adding the waves together, we create a unique wave. And the height of the wave, in this difference in pressure in the ambience, is the amplitude, meaning the loudness of the noise, the sound. And the distance traveled in seconds is the pitch of the sound. And actually, one more thing about this thing. Let's say there is a 20 Hertz sound. What does this mean is it makes 20 cycles in a second, and sound moves a long distance in a second. So it means that a sound wave of 20 Hertz is actually quite noticeable in the real world. So for example, some of the sound waves of the bass could be a wavelength of, for example, 1 meter. So there are a lot of interesting things happening in this field as well. If the low noise is coming from directly in front of us, we may not even hear it. But if we move just 50 centimeters away, we could hear it in full blast. So this is the kind of like the cycle from one high point to another high point or low point. It's a cycle, and it's also called the frequency. I guess that's about it for now. Thanks for listening to my little ramble about sound waves. I hope you found this interesting, and thanks for watching. Bye bye.